Over the past few years, one thing in AI has kept growing non-stop: the size of context windows. First, it was 8,000 tokens, then 32,000, then 100,000. And now people casually talk about models that can handle 1 million tokens or more. On the surface, this sounds like the final solution. Just put everything into the prompt and let the model figure it out. No limits, no trade-offs, no problem. But real-world use tells a very different story. As context windows grow, performance does not improve forever. In fact, it often gets worse. Answers become vague, reasoning breaks down, costs shoot up, and at some point, the model simply loses focus. Instead of becoming smarter, it becomes overwhelmed. This gap between what looks good on paper and what actually works is what pushed researchers to rethink a very basic assumption. What if the problem is not how much a model can read at once, but how it reads at all? That question led researchers at MIT and later Prime Intellect to a completely different approach called Recursive Language Models, or RLMS. This is not a bigger model, not a wider window, not a compression trick. It is a shift in how language models interact with information. Instead of forcing the model to absorb everything at once, RLMS treat the input like an external world, a world the model can explore step by step. To understand why this matters, we need to look at the core problem modern models face. Even the most advanced models today suffer from something researchers now openly call context rot. As inputs get longer, quality drops. And the drop becomes much steeper when the task is complex. If the task is simple, like finding one keyword inside a long document, models do okay. But if the task requires comparing many parts of the input, or reasoning across relationships between them, performance collapses. This shows up clearly in benchmarks like oolong and oolong pairs. These are not retrieval tasks. They require transformation, aggregation, and comparison across large inputs. In the MIT paper, researchers visualize this problem using GPT-5. As input length grows from a few thousand tokens to hundreds of thousands, GPT-5 performance drops sharply. On linear tasks, the decline is noticeable. On quadratic tasks, it is dramatic. In oolong pairs, which requires pairwise aggregation across the input, GPT-5 almost completely fails. F1 scores fall close to 0 even before the hard context limit is reached. This tells us something important. The issue is not just running out of tokens. The issue is how the model processes information. Traditional models are forced to load everything into their working memory at once. Once the prompt is inside, the model has no control over what to focus on and what to ignore. Everything competes for attention, all at the same time. RLMs flip this idea upside down. In an RLM setup, the massive input does not live inside the model. It lives outside in an environment. Think of it like a giant document sitting on a desk. The model does not read the whole thing. Instead, it is given tools to interact with it. The model can skim sections. It can search for keywords. It can extract small chunks. It can take notes. It can even ask smaller helper models to analyze specific pieces. The key idea is that the model only looks at what it needs, when it needs it. A simple analogy helps here. Instead of memorizing an entire book, the model flips pages, highlights important lines, and asks an assistant to summarize a paragraph when necessary. The main model stays focused on reasoning, not storage. Behind the scenes, one primary model runs the show. This main model connects to a workspace where the full input exists. It can run searches, split data into chunks, and delegate parts of the work to smaller, cheaper models. Once it has gathered everything it needs, it assembles the final answer and returns it to the user. From the outside, it still feels like a normal chat. One question in, one answer out. But internally, the process is completely different. This shift changes how models think. Instead of worrying about how much fits in memory, the model focuses on how to navigate information. And that difference becomes critical when inputs are massive. One benchmark makes this especially clear. In this test, the model receives up to 1,000 full documents at once. That is millions of words. No traditional model can read all of that directly. It is not even close. With an RLM setup, the model does not try to read everything. It searches, scans, and zooms in only on relevant sections. Everything else stays untouched in the background. That is the real breakthrough. Input size stops being the main bottleneck. What matters instead is how intelligently the model explores information. The results back this up. When RLM is paired with GPT-5 on this benchmark, accuracy reaches just over 91%. The average cost per question stays under $1. In comparison, forcing a base model to process everything directly would cost between $1.5 and nearly $3 per query, assuming it even works at all. And the gap becomes even larger on harder tasks. Take code QA from Longbench v2. GPT-5 on its own reaches about 24% accuracy. Adding a summarization agent improves that to around 41%. But switching to an RLM setup pushes accuracy to 62%. Then things get even more interesting. In an ablation study, researchers removed recursive subcalls but kept the external workspace, called the ripple environment. This version reached 66% accuracy, even higher than the full RLM in this case. That result sends a strong signal. Simply moving context out of the model's head and into an external environment already provides huge gains. Even before recursion plays a role, the model performs better when it is not overloaded. Now look at the most brutal test, U-long pairs. GPT-5 alone scores around 0.04 F1, which is essentially useless. Summarization agents stay near 0. A retrieval-based system reaches about 24.6. The full RLM jumps to 58. Even the ripple-only version with no recursion reaches around 44. For Qwen 3 Coder, a large open model, base scores stay below 0.1. With RLM, it reaches over 23. The pattern is clear. Externalizing context prevents overload. Recursive calls allow reasoning in manageable chunks. The MIT paper also shows what RLMs actually do step by step. And once you see it, the behavior feels natural. First, the model takes a quick glance at the input, just enough to understand what kind of data it is dealing with. Is it code, logs, documents, tables, or something else? That initial scan helps it choose a strategy. Next, it becomes selective. Instead of reading everything, it searches for patterns, keywords, and relevant sections. Large portions of the input are ignored completely. When complexity increases, the model stops trying to handle everything at once. It breaks the input into smaller pieces, like individual documents or lines. These pieces are processed separately, often by helper models. The main model stays in control, collecting results and combining them. Even output length is handled differently. When the final answer is very long, RLMs do not generate it in one go. They build it piece by piece, saving parts and assembling them at the end. This avoids traditional output limits. On average, RLM runs are surprisingly competitive. In many cases, the median RLM cost is lower than a single large model call that tries to do everything at once. But variance is high. Some runs are cheap, others burn budget through too many subcalls. The authors note that current implementations are basic. Calls are synchronous. There is no parallelism. There are no learned policies for when to stop. This leaves a lot of room for improvement. This is where Prime Intellect enters the picture. They took the MIT blueprint and built a concrete system called RLMNV. Their design choices are very intentional. The main model only interacts with a clean workspace. No massive tool outputs, no raw web pages, no noisy data flooding memory. All heavy tasks, like web search or file access, are handled by smaller helper models. The main model focuses on reasoning and planning, not digging. They also introduce batch execution, allowing the system to send many small tasks at once. This speeds things up significantly. At the end, the model must write its final answer into a specific location and explicitly mark completion. No half-finished thoughts, no wandering. This separation turns out to be crucial. Large chunks of text never enter the main model's memory. Only summaries, notes, and intermediate results do. This keeps everything manageable. Prime Intellect tested this setup across several scenarios. Deep Dive focuses on noisy web research. MathPython tackles competition-level math using code. Oolong is reused directly. Verbatim copy tests whether the system can reproduce complex data formats like JSON and CSV. Across these tasks, models like GPT-5 Mini and Intellect 3 MOE became noticeably more reliable when wrapped in the RLM structure. Comparing models reveals something even deeper. GPT-5 and Qwen 3 Coder both improve under RLMS, but their behavior differs. On BrowseComp Plus, RLM with GPT-5 nearly solves the benchmark. RLM with Qwen 3 Coder struggles on many tasks. The system prompt is almost identical. The only difference is a small warning telling Qwen 3 Coder not to overuse helper calls. That tiny change leads to very different behavior. GPT-5 is cautious. Qwen 3 Coder is aggressive, splitting tasks line by line. Sometimes the model overthinks, burns budget, and still gets the answer wrong. But this is also where the upside lies. The paper argues that RLM traces represent a new form of reasoning data, and reasoning data can be trained. With reinforcement learning, models could learn how to explore efficiently, how deep to recurse, and when to stop. So when people ask whether AI agents will handle massive codebases, full company knowledge graphs, or months of logs without forgetting critical details, this is one of the clearest answers so far. Now the question is yours. Do you think this makes context windows less important or just changes how they are used? Drop your thoughts in the comments. If this helped you understand what is really changing under the hood, like the video, subscribe for more deep dives like this, and thanks for watching.